Hey everyone, it's Eugene, and welcome to Forensics Talks. We're back again for another episode. And just before we get started, just want to get through a couple of small things here and some simple announcements. So depending on where you're watching from, I'm going to look at the comments here. And I want to make sure that people let us know, what city are you watching from? Are you over in Europe? Are you in South America? Are you in the US? Where are you? Just go ahead and type that into the comments there. Always like to know where people are watching from. Also, don't forget, if you're interested in Forensics Talks and you want to see more of these, just hit the like and subscribe and the little bell, and you'll get notified every time. I've been trying to do these a little bit more. It's been difficult just because it's been so busy. But anytime we do schedule another episode, you'll be informed right away. And I try to post them on social media and everything else. We're going to be using the chat window today for everybody to converse. And if you also want to ask a question of our guests, so go ahead, you can type that in. And what I'll do is I'll have a look at that as we move along and make sure that your questions get answered. And so I can already see people here. Okay, we got Florida, we got DC. Wonderful. Hey, thanks so much. Thanks for chiming in here. Just a couple of quick announcements here. Let me see if I can share my screen. Okay, just before we get started, we'll get a chance for people to get caught up because I know people are at work and they got to catch up and get to their computers and stuff. So this one is for Recon 3D. So if you are interested in iPhone scanning, okay, if you didn't know that the iPhone Pro versions have a little LiDAR scanner sensor in there, you can use it for 3D scanning. And so Recon 3D is one of the foremost apps and probably the most focused app for forensics. And you can find out a lot more information at Recon 3D. Let me bring that up here. Okay, so it's at recon-3d.com, and we are having a training class. So there's actually a certification class for Recon 3D, and we go through all the basics, best practices, we go through the technology, we go through accuracy studies using accessories, all that sort of thing. And that's next week. That's June 12th. Okay, so you have to go to the website, just go to the training section, and if you're interested in signing up, have a look over there. Okay, no problem. Also, with respect to Vision 3D, actually, and yesterday, well, I should say Recon 3D. So yesterday we just released a new version, a little update. So that's a new thing, but also Vision 3D. So I don't know if any of you are aware, but on the Recon 3D website, there's also a Vision 3D page. And if you head over to Vision 3D, you'll see that there's a tutorial video. And that tutorial video will cover how you can take a lot of your 3D data, whether it's photogrammetry models or scan data. It doesn't matter where it comes from. It doesn't have to be from Recon 3D. It could be from a Faro scanner, a Leica scanner, whatever. But it's a way of sharing data in 3D. And if you want to learn more there, also you can go to the Recon 3D channel on YouTube. Okay, there's a couple of videos here. One is called Vision 3D Autopsy Tutorial Video. I kind of snuck that one in there just as a kind of an idea of how you can take 3D data and use it for an autopsy or to present findings from an autopsy. But I've also got the update tutorial from the IPTM crash, which was a couple weeks ago, I guess. And I show you how to package everything together in the latest version. Okay, so have a look at those, have fun with it. And what else do I want to talk about? Oh, yeah. So I want to talk about the IBPA. We're going to be talking about bloodstain patterns today and HemoVision. And so why not talk about the IBPA? So the International Association of Bloodstain Pattern Analysts. There's going to be an upcoming conference in October of this year. So it's just on their website, October 7th to 10. It says Garden City, Idaho. And I've been a regular attendee the past while. But if you are doing any work with respect to bloodstain patterns, bloodstain pattern analysis, classification of patterns, whatever that might be, crime scene investigation, this might be an interesting conference for you. A lot of great people there. Some people who have been just focusing many efforts in this particular area for a very, very long time. And so you can learn a lot from some really, really great people over there. What else? Okay, Pixel Scale. So that's a little app that I released not too long ago. It's free. It's on the App Store. I don't want to say too much about it, but if you look for Pixel Scale, okay, it's this guy right here. That's what the icon looks like. And what this will allow you to do is import an image from your gallery or your photo library. And if you have a ruler in there and you've taken a 90-degree photo or an orthogonal photo, you can basically scale the image and then measure other things inside of the photograph, okay, beyond the scale. So just a little fun app for a little personal development project, but just letting people know about it so they can download it and have fun with it as well. Okay, so we'll leave it there, and we're going to move on. Okay, and get right to it. And I can see that there's some other people who have been joining us. Okay, so look, welcome to Forensics Talks. This is episode 108, and my guest today is Philip Joris. And Philip is from Belgium, and he's the co-founder of Forentrics, and it's a startup developing advanced software for crime scene investigation. He holds a master's degree in areas like electronics and artificial intelligence, and he's earned a PhD in electrical engineering. During his doctoral research, he developed some new techniques for bloodstain pattern analysis and also virtual autopsies. I definitely want to ask him about that. And all of this work led to the creation of HemoVision. Okay, so the company is Forentrics, and this is their flagship tool. And it's something that I'm quite familiar with and something that we're going to be focusing on today. So let me go ahead and bring him in here. There he is. Philip,
Hi.
all right.
Hi, Gene.
All right. So full disclosure for everybody. So I've known Philip for at least, I don't know, it's got to be like 8 years, Phil. I'm not sure what we're getting to. Yeah. Okay. So, and we've worked quite a bit together. So, sometimes when I bring people in here, I don't really know them very well, but I know you fairly well. And I think you know me very well. We've done workshops together. We've done a bunch of stuff. And I keep asking myself, when did I actually first meet you?
I think maybe the BPA in Canada.
In Ottawa. So that
Ottawa?
was that 2017 or something like that? I think
17 or 18, yeah.
Well, 18 was Paris, wasn't it? Or was it 2019 was Paris? Was the IBPA conference? I don't know. I remember we went for a walk in Paris and or at the conference there we had a good chat at lunch. So anyway, all good. All right. Well, let's get started here. I want to ask you about your background and how this all got started. And obviously, electrical engineering. Hey, just so you know, I did 2 years of electrical engineering, and then I couldn't stand it, so I switched over to aerospace, and that was a lot more interesting for me. So, but I know what you have to go through in electrical. But can you kind of walk me through, what maybe what you thought you were going to be doing at first, and then kind of how you ended up coming out of this with HemoVision, let's say.
Yeah. A long journey. As you said, I'm indeed an engineer in electronics and ICT. And I think it was during those studies that I actually kind of developed a love for programming, and more specifically like computer vision and teaching computers how to understand stuff and make decisions. And after that master's, I decided to do another master's specializing in artificial intelligence to deepen my knowledge in that field. And at the time while I was studying, I was actually watching a very popular BPA series called Dexter. Pretty sure a lot of people will be familiar with that. And at the beginning of the year, all of the students, they get a list of a lot of thesis topics that they have to select a thesis topic from. And one of the topics in the list said, hey, we want to do something with bloodstain pattern analysis and artificial intelligence. We're not sure what we want to do, but we want to do something with it. And I was like, I'm in love with the series. Why not go for it? And yeah, that's basically my first steps in AI and combining it to with forensics. And yeah, things just grew from there. I finished my master's, and my promoters at the time, they were actually like, hey, are you interested in doing a PhD where you work on the overlap between forensics and engineering? And I was like, yeah, hell yeah. And that's how it all got started. Yeah.
Excellent. So, and I saw that you had some work with this virtual autopsy stuff. So what was that about? How did that get started?
Yeah, so part of the PhD was on bloodstain patterns, and the other part was indeed on virtual autopsies. So the goal was to, instead of using the traditional invasive autopsy where you put a body on the table and actually just cut it open and look for stuff, maybe we can do some searching for anomalies on CT scans. So in the hospital where I worked, it's quite common for bodies to be scanned in the CT scanner. And I was developing an approach that was general enough to detect like any type of anomaly, not focusing on one specific anomaly, like a specific type of tumor or something. But I was looking at a more general approach. And the goal there was to apply it to gunshot trauma, because it's very diverse. There's bone fragments, there's air bubbles, there's pieces of metal from the actual bullet. So the appearance of the anomalies is very, very diverse. And in the end, I developed a method that could detect all of these anomalies and then try to link them all together to determine the trajectory of the bullet inside of the body. Yeah, fun. We
That's
had a lot of fun experiments.
yeah, super cool. And actually, you did. I think I remember hearing about this from Erwin. Erwin
Yes.
Borges. Yeah, he's
Yeah.
retired since, but great guy. And so you had to shoot at all these.
Yeah. So we went to a local butcher in the morning at 5 a.m. We picked up some sheep heads, and then we put them through the CT scanner. We went to shoot at them with a low caliber rifle, and then we scanned them again. So we had a before and after, and that was basically my training data or my testing data on which I could develop and test my algorithms. Yeah.
The things we do for forensic science, eh?
Yes.
Yeah. And there's always a butcher involved for some reason. I don't know.
Yeah, and they were still nice and warm. It's a very special memory. Yeah.
Right on. Well, let's talk about let's get into the bloodstain pattern analysis and like some of the things that you were working on initially. So like just before, well, let me ask you this, like at what point did it sort of hit you that you said, you know what, I'm going to start this project where I'm going to put together this bloodstain, pattern software. And so, what was the trigger that said, hey, we need something like this? Like, were you talking to people in the area and they said, hey, we really could use a new tool like this? Or how did that come to be?
Yeah, so the the starting point, as I said, was the master's thesis, and this was in close collaboration with the forensic department of Leuven in Belgium. And at the time, there was Els. She was at the time a bloodstain expert, and she was actually doing crime scene investigations, doing the BPA. And talking with her and learning what it was all about, I tried to develop methods that could actually help her do a better job, make her life easier as a BPA expert. And at the time, it was just like, hey, this is cool from a research perspective. Like, how can we take certain steps of the whole BPA process and use AI to automate this or make it more accurate or more objective? And that was from a research perspective, like really cool. But then we started interacting with like the federal police in Belgium, and they also saw a lot of potential in the software. I also did some conferences. So like my first IBPA meeting was in Rome, 2014, if I'm correct. And as a newcomer, it was all very overwhelming to see all of the people doing their amazing BPA work. But the feedback I got on even the very earliest steps of HemoVision was so overwhelmingly positive that I said, okay, maybe we should take another look at this and develop it a little bit further and make an actual product out of it.
Yeah, and I think what's interesting is, I don't think there's very many electrical engineers that are, people studying electrical engineering that are into the whole BPA world. So I think bringing a fresh perspective like that is really helpful. So were there any things at the beginning that you found out about, BPA or whatever that sort of opened your eyes and said, oh my God, like there's opportunities here, or maybe some things that may have surprised you, or maybe something that you said, oh man, I can solve this problem. You know what I mean? Like I can do something here. Like what were some of those things maybe that hit you early on?
Yeah, there's quite a few things, but the thing that struck me most was that a lot of the work is still highly dependent on manual work. Like there's a lot of manual steps. And when talking to Els, like the BPA expert from Leuven, they had to do so much work just to get, for example, to the result from an area of origin analysis. They had to perform so many measurements. When they initially explained stringing to me, I was like, wow, this is weird. Why would you actually do this? I mean, there's got to be a better approach. Then I learned that people don't actually string anymore. They use tangent method, etc. But still, it's a lot of work getting to a single result. And I thought, well, maybe we can automate certain parts of it and make life easier.
Yeah. So, and I think, well, talk to me about the automated process or the simplification of the documentation process in HemoVision, because you take a different approach than other softwares, which are, let's say, a lot more manual. So maybe can you describe what you're doing there in HemoVision?
Yeah, sure. So whenever we're doing, for example, an area of origin analysis, we want to analyze the convergence of multiple trajectories from multiple bloodstains. So we need to place them all in a same frame of reference. They have to be in the same space. And what people typically do is they measure the coordinates, like they take a reference point somewhere, the corner of the room, and then they just measure what the horizontal and vertical offset is. But instead of doing all this measuring, I thought, let's just reconstruct the whole scene in 3D and get the measurements automatically in this 3D space. And that's exactly what we're doing with HemoVision. So we rely on photogrammetry, which I think a lot of people are familiar with. So we take a few photographs from different perspectives, and from these photographs, we can then reconstruct parts of the crime scene in 3 dimensions, and we can take accurate or fairly accurate measurements in this space. That's one of the aspects. Yeah.
You have, so for example, you have these markers that you place on the wall. Like, so you have, like there's one larger one and then there's like these little ones. So can you talk to me about these markers and what their function is?
Yeah, so when we initially started to develop methods for the reconstruction, we said, well, photogrammetry is a great example of how you can achieve a good degree of accuracy regarding 3D reconstructions. But there are certain cases where photogrammetry runs into difficulties. And this is the case, for example, when there's very little texture on the walls, when you have plain white walls. And that's typically what we have in a lot of homes. People just paint their walls in a single color, and the bloodstains are too small to give you sufficient texture and key points to reconstruct. And then we said, let's make the approach more robust, because we want to make it so that it's applicable in each and every case and not just 50% of the cases. So we have these little checkerboard patterns. They resemble somewhat what you have in the back, in your background. And we place a few in and around the spatter pattern, and then the software can accurately detect those and use those to reconstruct the scene in a more robust way. They have different functions as well. They provide scaling information. You can also take photographs freehand, so you don't have to be perfectly orthogonal to the plane, like frontal parallel. Any perspective distortions are corrected using these markers. So they have a lot of functions, and they help us a lot, to achieve this automation.
Yeah, so the user or the person that's setting up the crime scene, the basic process is going to be to place those markers in areas of importance, like where the bloodstains are, and then now in terms of measurements, how many measurements do they need to take then?
Typically, we only require one. So we have one larger overview marker, as we call it, and it's used to position the pattern as a whole in 3D space. And you just take one reference measurements to this overview marker from your chosen reference point, for example, the corner of the room. And this is just to position the pattern as a whole in 3D space. So other than that measurement, there's no manual measurement involved.
Okay. Part of the process that you have, though, is like you have to take photos for the overall pattern, like like there's like an overview marker that you have, or you want to get all those markers in, but then you also allow individual photos for like those smaller detail markers, so you can see the smaller bloodstains or whatever. So like, can you give any recommendation on the number of photographs or the way that you would photograph for the overview versus the detail, and like how many photos are we talking about usually?
Yeah, sure. So for a fairly normal, like a normal scene, just a few corners, the corner of a room or a few surfaces, because this is one of the new aspects of HemoVision. So you can place these markers on all kinds of surfaces. They can be arbitrarily angled, and HemoVision will reconstruct them all in the same time. We recommend taking like 15 to 20 photographs maybe. And you don't need to capture all markers in all photographs. They just need to be each marker needs to be in a few photographs. So let's say 15 to 20 overview images. And then you just take as many detail images as you need. I typically say that a detail image covers roughly about a 50 by 50 centimeter region, so half a meter by half a meter, depending on the resolution of your camera, of course. And then you can take 1 or 2 detail images per detail marker. And I would say for the most scenes that I've processed, between like 10 detail markers, maybe 15 if it's a very, very complex one with a lot of different surfaces. So all in all, maybe 30, 40 photographs.
Okay, so again, between taking the measurement and taking 30, let's say 30 photographs or something like that, then it might take you 5 minutes, right? Like 5 minutes or 10
Yeah,
minutes or something like that.
right.
So it's a pretty okay. So that's a significantly reduced time to document this pattern, which is pretty great. So that's awesome.
Yeah, that's
Um,
it's a quite fast process, and it also has the advantage that the person who takes the photographs doesn't necessarily need to have like the most expertise about BPA. So it can be somebody else that takes the photographs. They just need to know how to place the markers, take the photographs, and then somebody else can do the analysis in HemoVision. So all the information that is needed for the analysis is in the photographs because of the markers, because of the way we take the photographs.
right, and I guess you should be clear. Like you're talking about strictly for the pattern analysis. It's not a replacement for the regular crime scene
Of
photos or
course,
anything like that. Yeah.
of course,
Okay.
yeah.
Okay.
Yes.
And then you take all this, you take the images, you bring it into the software, and the process is just, I mean, you're setting up a project. I mean, how long does it take to process something like that on a computer, on a decent computer?
Well, it kind of depends on how experienced you are. A few months ago, I made a video where I processed the scene in like 2 or 4 minutes, I believe. If it's a bit more complex, let's say 15 minutes, 20 minutes, depending on how many bloodstains you select.
Right, right,
But
right.
it's a fairly fast process, yeah, fairly
Yeah,
quick.
and but the image on the structure from motion, the photogrammetry part there, I mean, that can be done usually in a few minutes.
Yeah, sure. Yeah,
That's pretty quick. Okay, cool.
yeah,
Let me ask you about bloodstain marking, because part of the process traditionally has been that the analyst is going to take an ellipse and they're going to take this ellipse shape and they're going to mark it over a bloodstain,
yeah.
fit it to the, get the proper angle and all that sort of thing. So there's something that you did it's actually on your website too, and I should probably bring it back up here, but it's a little bit of a different approach to marking, and some of it is automated and some of it is like semi-automated. So I think it's under here, under news at the bottom. But here it is. So it says statistical impact stain analysis. So this has something called a shape model, and you've written a paper on this as well. So you
Right.
published a paper. So
Yeah.
explain to me how this is different, or explain to everybody how this is different than the regular old marking an ellipse as best as you can get it.
Yeah. So this was actually part of the early works that we did on HemoVision. So like the core algorithms. Um, so as you said, traditionally, people just assume that a droplet is perfectly spherical, and when you project it onto a flat surface, it becomes a perfect ellipse. Obviously, we know that there's different factors involved when the blood droplet oscillates in the air and contact comes in contact with the surface, etc. And we said like, hey, instead of assuming the shape of a bloodstain to be elliptical, why don't we learn the shape of a bloodstain and then link it to its impact angle? So what we did is we created a database of, I think, a little over 400 bloodstains. And for each of these stains, we knew the exact angle at which it impacted the surface. So we know that this shape of this bloodstain corresponds to this angle. And then we used something called principal component analysis, which is basically just a dimensionality reduction technique that can be used to learn how the shape varies across your data set. So we sampled the outline of each of the bloodstains, so just the contour of the bloodstain. And we learned how this contour changes with impact angle. And the approach, the advantage is that we do not need to assume anything. The data will tell us what a bloodstain looks like. And then we can apply this bloodstain and transform it and deform it so it fits onto a new bloodstain in a new image, and then we can get its impact angle from it.
How do you handle bloodstains which sometimes are malformed on the back end? So you may have a really long tail, you get all these little, defects. Sometimes, you hardly get the front end is really nice and then the back end is all a mess. So is there how did you approach that?
Yeah, so that's one of the difficulties that we have with ellipses. So typically when people mark the front and the back, the front is very clear. It's the tip of the bloodstain, but the back is not clear. And there's some kind of region where it's not very clear where the bloodstain should end. So our model is not really a closed contour. It's like an open-ended contour, like an inverted U shape. So it basically fits around the bloodstain by primarily focusing on the front of the bloodstain and somewhat automatically ignoring the tail information, because the tail for the impact angle has no relevant information. It can be used for the direction, but for the impact angle, it holds no information. So the model automatically ignores these tails, and that's just because it's open-ended.
Okay. So were there any, I'm just curious now because we're talking about, machine learning, and I don't know, somehow I think I'm gonna have to slip in the AI word, but
Yeah.
yeah. But were there any, just, for out of curiosity, were there any challenges with working with data sets like that, with teaching it? Because I mean, in reading here, I mean, you have to do 2.5-degree increments, right? You need a lot of images. I mean, is this something that you can continually update if you like, you can keep throwing more data to it? Like, what were some of the challenges with using this type of technique?
Yeah, so I think the technique we used is more like statistics. So with only, let's say, 400 examples, we could get really accurate results. In hindsight, we probably could have used a little less data because the technique we use is so powerful and it's just basically pure statistics. I think if you're going to move to different models, like if you're throwing in the AI word, if we're talking about deep learning, for example, we've done some experience with that as well. 400 examples is not going to get you anywhere. So you would need a lot more, and you would need to apply some data augmentation. And I think there's other challenges there as well. I think one of the key values that we have is trying to have explainable models that we can explain how they get to a result and why they get to a result. And that's something that's very more difficult with deep learning. So in terms of data collection, it was actually quite straightforward. One of the difficulties we actually had was trying to convince people that it actually worked.
Oh, really?
Yeah, I think one of the first comments at the very first presentation I ever gave about this model, I think was at the BPA, where one of the first comments was, "Why would you do this? We've been doing ellipsis for over 60 years." There's no
Yeah.
real answer. I said, "Well, I just want to try something different." That was my answer, I think. But anyway.
Yeah, that was because it was before GPT. That's why. If it was after
Yes.
GPT, people would have been more accepting of it, I think. So, well, one of the functions, and it's not something that we typically see in software right now, but one of the main functions of a bloodstain pattern analyst is pattern classification. And since we're talking about, this
Yes.
sort of thing, have you thought about tools that could assist an investigator on classifying different types of patterns? How would that work?
Well, funny you mentioned, but we're currently doing some research on that, obviously. So we're looking at how can we support the BPA experts in classifying. For as long as I've been going to these IBPA conferences, there's always been discussion about classification because everybody does it differently. Everybody documents their patterns differently, I think. Everybody has their own standard operating procedures. And we want to see if there's some way we can support the forensic expert. And I think if you're dreaming about AI, you could just throw it a picture of a random bloodstain pattern, and it's going to say, hey, this is the type of bloodstain pattern that you're talking about. This is probably the mechanism, all kinds of information. But I think maybe that's going a bit too fast. I think there's more. I think there's intermediate steps we can take. One of the things we're, for example, looking at, OSAC has like this perfect decision tree that can help you to go through all of the characteristics of bloodstain patterns and come to a conclusion based on a standardized document that's accepted by a lot of people. I think if we can develop tools that include these kinds of documents for experts, I think that's a pretty good first step.
Okay, so it's like workflows and guidelines and sort of walking through a process of going through. And so there's this, so at first it's not like hands off, everything, the machine does everything, the computer's doing everything. It's interactive and really assisting more than taking over. Yeah.
And I think this can then be combined with other techniques. Like a lot of people, I think, just they dump all their photographs in a report like a plain PDF document, and I think that's fine. They are typically very descriptive in how they describe the patterns. But if you can combine everything into the 3D environment where you locate all of these patterns in their correct location, and you can do fly-throughs and maybe use virtual reality to bring this to court, I think there's a lot of different options there as well.
What kinds of patterns are you able to do with HemoVision?
So right now, I think we tested our methods on pretty much all projected bloodstain patterns. I mean, airborne ones. So we initially started with spatter patterns resulting from an impact to do area of origin analysis. We've also tested these techniques on cessation patterns, expirated patterns, because they're all projected blood with an origin, you could say. And then we're also recently, we've been developing the cast-off module. So whenever you have a bloody object and you swing it, blood will typically be released from this object, and it deposits like a linear pattern. And we're now developing a method that from this pattern can actually reconstruct a swing trajectory, not just the swing plane, but also the trajectory. So we've implemented this as a beta feature in HemoVision, and we're still doing some validation to make sure that everything is working correctly and that we have known error rates and those kinds of stuff.
Okay, I got an example project here, so I want to bring this up on screen so people can see here what I'm talking about. This one was a you can see the images. So folks, if you're looking at my screen, actually let me shrink this down a bit. You can see that there's some images here, so if I can flip through these images. So this is interesting because this is not a typical, flat wall and easy to measure from. We have slanted objects here, things on different planes and such. So if you had to measure that by hand, it becomes very difficult. So this is a would you call it a multi-surface project kind of thing?
Yep.
Okay.
Yeah, it's really funny that you mentioned that, because when I was reading all the literature, most of the experiments are people creating these kinds of patterns on a single vertical wall, and that's how we developed HemoVision. And we were like, we've got it all down, we've got it developed, we've got a nice interface, let's get it to the world. And then I had the opportunity to attend 2 crime scenes with the federal police in Brussels, and then I get to my first crime scene, and there's just blood everywhere. It's on all different kinds of surfaces, tables, walls, and I was like, well, this is going to be difficult. And then we really started developing, and then this is the result from that experience.
Yeah, excellent. And like you can flip through, I can see here, you can flip to a 2D to a 3D view and that sort of thing. So let me bring up another one here, because this is a cast-off pattern. Let me go to the 3D view here. But this is one that we actually did together at actually it was in Kansas City, and IBP in Kansas City. So this was actually a cast-off pattern, right? So and well, what can you tell me about what's going on? You explain it to what people are seeing here.
Yeah, so the red lines are the estimated linear trajectories of the bloodstains. And then the tube, I think it's been coined noodle at the conference, so let's call it the noodle for now. The noodle actually represents part of the flight path that was made by the swinging object. I think if you do some more stains on top, the tube will expand, but this was definitely a very, very nice example. I think we had just developed this method at Kansas, and it was a very nice environment to test this new approach. It was really fun.
Yeah. Yeah, I love the fact how you can visualize all these trajectories sort of going through this little volume, this tube with the noodle. And I'll probably have to give Irv Albrecht credit for that, because I remember him from Toronto. I remember him saying, it might have been, I think he said it was a noodle. And I didn't think about it like that, but hey, I'll give him credit for it.
Yeah.
But so this is, if you had to define this, I mean, it's not like area of origin. So if we maybe let's do that. Let's describe, or if you can describe for me, what does the area of origin tell us? So if I flip back to this project, you got this egg looking thing here, right? Versus what this noodle is telling us here, right? This tube and all these lines that are going through. So if maybe we'll start here with the area of origin. How is this being defined, or how is this classified?
Yeah, so this one, when we're doing area of origin analysis, we're assuming that the bloodstains are coming from a common area of origin. We're not talking about a point, but rather an area, because it's always a dynamic event. And so this could be the result of a beating, for example. Obviously, this was created by using an impact device that we made. So there's an impact into liquid blood, and the blood is then dispersed through the air to surrounding objects, walls. And we can calculate backwards from these trajectories. So the trajectories are also in red here. And the area of origin indicates some kind of statistical region wherein the area of origin should be.
Okay, and let's switch. Let's go to here. Let's go to the cast off example here. So how is this different now? How is it being calculated?
Yeah, so this is different in the sense that the object that's releasing the blood is actually in motion. So I think you used, I don't know, was it a knife or a hammer or something, or no, just like a plastic stick, a wooden or something like that?
Yeah, it was some kind of a rod or something like that. I can't even remember right now. Yeah,
that was drenched in blood, and you started swinging it at a wall. And I've got videos of it if you want them.
yeah, I think we do somewhere. We've got some different things going on.
As you swing the object, the blood is actually released in a somewhat circular motion or radial motion. And in this case, we're not calculating back to a single area of origin, but more towards the whole trajectory of where the blood has been released from. We're doing some nice validation, or you're doing some nice validation on it. I think it's looking promising.
It is in fact. I don't know why I have this interest in cast off, but yeah, it's really interesting what we can do. And I think it's, the fact that it's just another way of defining, this other mechanism, and saying something about it.
Yeah, if you go to the right on the property view, you can turn on the plane. I think there should be a checkbox to enable the plane.
I think I might have I got a special version. So
okay. No worries. So typically you could also visualize the plane, which is the 2D plane in which the object was swung. So somewhere within this plane, an arm was swinging or an object was swinging. So there's different kinds of ways to visualize this. And I think the tube is one of it. And again, the width of the tube just represents some kind of uncertainty similar to the area of origin.
Okay. You have this AR image. Can you explain what the AR image is doing here?
Yeah, so the augmented reality we have is one of the things we focus on to make evidence more easy to present in court. So if you have a 3D scanner and you scan your crime scene in 3D, you can import this into HemoVision and show your results in the full context of the crime scene. And this is very good for presentation purposes. But not everybody has a 3D scanner. So we thought we still want to be able to include like the full context of the crime scene. So let's develop some kind of augmented reality. And what it does basically is we have just a plain standard photograph, and we're going to estimate the position of the camera with respect to our scene that we have, and we're gonna overlay our results on top of this photograph. And this is basically as if you would have used strings in real life. And this allows you to get some kind of context, crime scene context, or most of it, but without having a 3D scanner.
Yeah, no, I think it looks super cool because you're using the original photograph, so it looks realistic. You know what I mean? And you got these things coming out, so really, really nice. Good job there. Are there other things you could do with this? Like somehow, could you extend this to something that's like animated or moving? Or I'm not sure.
Yeah, so this is on a still image, and basically we could extend this method to video. We have done some experiments with it, so it's always more for augmented reality. It still remains a still image. It gives you a good idea, but it's still a still image, and it's difficult, or maybe difficult to interpret 3D. So if you're taking a video of your crime scene, you could basically do this for every frame of your video, and then you would be able to move around, for example, the body and see all of the bloodstains in the areas of origin. We do have a little bit of work there to make it process in a acceptable time frame. You don't want it to we don't want it to process for half an hour. We want it to be quicker. But we're definitely looking into that as well. Yeah, so you can just do this with videos as well.
Amazing. Okay. So tell me about the use of HemoVision right now. Have there been cases that you know of, maybe like where HemoVision has been used, or do you know different types of cases where it's been used?
Yeah, so I think one of our longest lasting partnership is with the Federal Police in Brussels. So they've been using it for 2.5 years now, I believe. They've done a lot of cases with it, and I think most recently 1 or 2 of them also went to trial. I'm not sure exactly when or how, but yeah, so they are using it operationally, and there's obviously other countries as well.
Yeah. So let me ask you, like, just based on where you are today, like, where do you see bloodstain pattern analysis using software like HemoVision, like moving forward to, or like, are they going to be integrating other types of things? Like, what kind of features or, evolving technology might be implemented in HemoVision in the future?
Mhm. Yeah, so there's a lot of different things on our list. We've got a lot of ideas. I think one of the main things is growing HemoVision by actively listening to our current customers. We get a lot of feedback from them, and that's really nice. Um, and Castoff was one of the things that was asked for us to, hey, could you research that a little bit? And so we're doing that now. But also the augmented reality on video is something we're working on. We're also getting some questions about nonlinear trajectories. So for those who don't know, so it's fairly common to use linear trajectories to represent the flight path of bloodstains. Um, but in reality, the bloodstains don't travel in a linear way. They travel in a nonlinear way due to drag and gravity and that kind of stuff. But we typically ignore it, and there are certain rules you apply to select bloodstains to limit the effects of drag and gravity. Nonetheless, in some cases, it could be interesting to have a method that incorporates gravity and drag, and we're looking into that as well. We've done some early research on it. Other stuff involves, so we've recently upgraded our software to include all kinds of 3D scans and mesh models, so you can all import these into HemoVision. Taking that a step further, maybe we can export it again into virtual or augmented reality glasses. Yeah, so a lot of ideas for HemoVision.
Let me ask you about the nonlinear trajectories, because I think that's an
Yes.
interesting area, because it's obviously trying to mimic the flight path of a bloodstain more realistically, more physically realistically, because the the linear trajectory makes some pretty broad assumptions. So normally, if you're doing, if you want to calculate something going through the air, you have to know a lot about mass, and you have to know a lot about the conditions, like that sort of thing. So have you done any experimentation with that already? Like, have you coded anything maybe on the side to like run through some scenarios? And how much can you get away with if you don't know a lot? Like, is it possible to document the scene conditions like people are doing right now with HemoVision, and then feed that in and maybe use that as a starting point?
Yeah, well, if we're talking about nonlinear trajectories, maybe we should shout out Daniel Attinger. I think he's the main
For sure.
expert in this field. So he has a method that incorporates quite a lot of physics, or a lot of physics in his methods. So I think he knows pretty much all of it. We have done some experimenting and coding ourselves, but obviously there's certain things that are difficult to get from a crime scene. I mean, for example, the volume of blood, it's very difficult to determine based on just the appearance of a bloodstain, because how much does the surface that the bloodstain is deposited on absorb the blood? Is there any shrinkage? All that kind of stuff. So we did some experiments where we make certain assumptions, and we also leave certain variables open, and we ask the software to optimize the whole system of constraints that we have. We have like 20 or 30 bloodstains. We have, for example, an area of origin coming from linear trajectories. We can put this all into a system, and we ask, okay, given everything that we can give you, what is the most plausible solution for nonlinear trajectories? And this is, again, more numerical optimization and looking for the best possible parameters given a certain scenario. We have done, I think I did a talk at the London IBPA, like the virtual one we had during COVID. But I haven't picked up the material since then, but maybe I should pick it up again soon.
I think you should, because it's that would be super cool if we can start getting some of that implemented without a lot of effort. I mean, if the workflow would be the same, where the user, the person is just documenting the same way, the photographs, putting in a measurement, and then making some assumptions. I think that makes a lot of sense. At least it would be closer, I think, to what's happening in reality, as opposed to these linear trajectories. Linear trajectories are useful, but they're also quite limited, right?
Yeah, if your bloodstains are still traveling upwards when they hit the wall, the overestimation of the height will be somewhat limited. But in some cases, you only have bloodstains on the floor, for example, that are elliptical, but they are on the floor. So it's very difficult to get an accurate estimate with linear trajectories. In those cases, I think nonlinear ones would be very interesting to have a look at.
Okay.
Yeah.
So we've talked about a lot of different things, obviously, but like, what is the next thing for you? What are you primarily focusing on right now for HemoVision? What's the next sort of thing you're going to implement? Or maybe there's more than one. I don't know.
Yeah, so all of that, I think many of the things we discussed already. I think one of the things is now growing HemoVision. We're getting a lot of positive feedback from our customers, and we try to also look at the small things. So we're looking at big things like cast off and nonlinear trajectory and pattern classification, but there's also like small tweaks and improvements we can make to the software that our customers like. So that's something that we focus on. Yeah, and for HemoVision, obviously, we've got tons of ideas, but we're also focusing on different areas of forensics. So as a company, Forentrics, we try to copy the vision that we had or have for HemoVision to other fields. Vision 3D, as you mentioned, is one of those. So we're looking at different areas as well.
Yeah. Hey, I got a question from Jeff here. He says, you could ultimately give information of length of arm object. And this is going back to when we were talking about the cast off. So
I guess, yeah.
yeah. So, and actually, you can say what you're doing in the software, maybe.
Well, yeah. So, hi, Jeff. I think you're in the right direction. I think we could get some kind of estimate of arm length plus object. And if you then know which object is used, you maybe could find out the arm length. So what we do right now for the cast off is, as a result from how I'm not going to go too deep into the method of how we actually determine the tube or the noodle. But what we ultimately get from the analysis is like a center point and a radius. And so this would be the pivot point and the length of the arm plus object. Yes.
Yeah, and it is something that you currently report, right, in the software, but it's still under beta. And I should give a shout out too to there's a student from the University of Toronto. That's Savita, Brickman Maxwell. So she's been doing some work in this particular area, quite a bit actually. And we're currently working on a study. Hopefully, going to wrap that up soon and get that published as well. Show people what we've got. So hopefully that will come through at some point.
Now, to the results.
Sorry.
I'm looking forward to the results.
Yeah, me too. We've got some blind testing that she's working on right now. So I went ahead and did some blind cast-off patterns, and now she's tasked with trying to interpret those and analyze them and see what she gets. She doesn't have the advantage of knowing where it came from now. So nice. That's the way it works. You mentioned about conferences and such. So do you guys get out every now and then to conferences? You're doing some training, like, what do you got lined up? You doing anything online? Are you planning anything to do online?
Yeah, so conferences definitely one of the IBPA is a yearly must for us. I think the last 4, 5, 6 years have been. It's always an amazing conference with amazing people, and I love coming back. So we'll definitely be there. We're doing other conferences as well, like ENSFI, the European conferences. We try to visit some customers here and there if it's close by. So any nice opportunity for us to interact with experts in the field, for us, it's always nice to learn from people. Yeah. Online, yeah, we do. On LinkedIn, we try to be active, and maybe in the future we'll do like a HemoVision webinar where people can learn more about HemoVision and provide us with questions and feedback, and yeah.
Let me bring this up here. So I just want to get this, but there's a contact form on the
yes,
on the hemovision.be.contact, and if you go over, just they can always get a hold of you here, right? If anyone wants to talk to you, right?
Yep.
Okay.
Perfect.
Do that.
Okay. Yeah. Send us an email.
All right. Excellent. All right, Phil. Well, I think we've covered a bunch of stuff here, and I know that you're going to be a busy guy in the near future because you've got some life changes happening.
Yes,
so
it's true. Me and my wife are expecting our first son, so it's first child. So it's exciting times. So this year is actually going to be born during the IBPA this year. So it'll be my colleague and co-founder Ruben who will be doing the honors of of attending the IBPA. So it's going to be a first for him, but it's going to be nice for him to meet all the lovely people I've been interacting with for years.
Yeah, Ruben is kind of a quiet guy sometimes. I don't know how to take him, but he's super smart. He's super nice. But
Yep.
he's been with you he's a co-founder, right? He's been with you from the beginning.
Yes, he actually joined the project somewhere 2000. Let me think, maybe 2021 somewhere. It's when we decided that we were gonna build a company from the university, but we had to do some more research, transforming everything from the research phase to an actual intuitive interface that is easy to be used. And he joined the project then, and he's been on it ever since, and he's a co-founder now.
So he was also from KU Leuven, and
yes.
Okay.
Yeah,
was he in the same program or different program, or where was he studying something different?
Different program. We had some similar studies, also the Master of AI, but then he went to work for a different startup company. But I hired him to do on the valorization track again at KU Leuven, and things just grew from there.
Okay. Well, he's a great guy, and I might have to get him in here one day. Maybe next time I'm going to talk to him about some of the heavy technical stuff he's been working on in the background. So that's fantastic. All right. Well, look, thanks so much, Phil. I appreciate it. We'll be in touch. We've got a lot to talk about, a lot of different projects we're working on together, but I really appreciate you being here. Thank you very much.
Thank you very much, Eugene.
All right. Hang back. Okay. I'll get back with you in just a second.
Sure.
Okay, folks, that's it. We are done with this particular episode, talking about bloodstain pattern analysis, HemoVision, IBPA. That's going to be coming up. And so if you have any questions for Phil, just go ahead and reach out. We will be back at some point in the near future with some more talks. I've got some things on body cameras. I've got some things on forensic anthropology, a whole number of different areas. So, hey, thanks, everyone. I really appreciate your time today. Have a great Thursday. We'll catch up with you soon. Bye-bye.